Hello everyone, my name is Juliana Morbec. I'm a lecturer in physics at Keele University in England. In this talk, I will discuss how you can tune the electronic and magnetic properties of monolayer phosphorene by doping and applying strain. So phosphorene is a very interesting material. It's a two-dimensional material, and it's a very interesting material because it's semiconductor and has a direct band gap. The band gap goes from 0.3 electron volts in the bulk system to 2 electron volts in the monolayer system. It's also very interesting because it has high hole mobility and it has high anisotropic optical and electronic and transport properties. And these anisotropic properties came from this puckered structure that phosphorene presents. So it has, when you look at the properties along the zigzag or along the armchair directions, you see an anisotropic behavior here for both for electronic, optical, and transport properties. For example, the mobility changes when you look at the armature direction or the zigzag direction. And it also has unusual mechanical properties. It can sustain strain up to 30% without break, and it's very promising for strain engineering. For example, you can tune the band gap or you can rotate the mobility by applying strain. For example, there's two figures that I'm showing here. On the left hand side, you see a change in the band gap of the system when you go from 0 to minus 12 or plus 12 strain along the zigzag direction. And you see that the value of the band gap changes when you apply strain, and also the nature of the band gap changes when you apply strain. You have direct band gap, the band gap that's direct with 0% strain, becomes indirect, for example, when you go from between minus 2 to minus 10% strain. And on the right hand side, you see that you can also rotate the mobility, the carrier mobility when you apply strain. With zero biaxial strain, you have, this is the red curve, you have high mobility along the armchair direction. And then this mobility goes down when you apply tensile strain, and up to 4% you have almost zero mobility along the armchair direction. And then in this case, the mobility moves to the zigzag direction, and then you see an increase in the mobility along the zigzag direction when you apply biaxial strain. So you can use, as this material sustains such a high value of strain, you can apply strain to change the properties of this material. And this is what we are doing here in this work. We are using first principle calculations to investigate how you can use uniaxial and biaxial strain to change the properties of this material, and how you can also combine this with single vacancies and carbon doping to tune the properties of this material. So just technical details here. Our calculations are based on this functional theory, and this is the exchange correlation functional you use and the code you are using in this calculation. But what's important here is that we did this calculation for a 4x4 supercell, which means that when we are creating defect or when you are doping, you are talking about a concentration of 1.56% of doping or defect concentration here. And here you see again, you have different directions, armchair and zigzag directions for the strain we are going to apply in the system. So let's first talk about single atom vacancies. So here we have pristine 4x4 monolayer phosphorene, and then the most important atoms here for this talk are these atoms labeled A, B, C, and D. And when you create a vacancy, we are going to remove this atom A, and what's going to happen is there are two configurations that can result here. So you can have this atom B moving in such a way to bond with atoms C and D in a symmetric way. So at the end, you have what you call configuration SV for single vacancy, 5566. 55 because you have two pentagons here, and 6, 6 because we have 2 hexagons here. And this is a symmetric configuration. And at the end, this configuration is non-magnetic, it's metallic, and has a formation energy of slightly above 2 electron volts. Another configuration that you can have here, it's what you call the SV59. That's an asymmetric configuration. Well, atom B doesn't move that further to bond with atom D. It bonds just with atom C. And then at the end you have an asymmetric configuration, what you call 5-9, because you have a formation of pentagon and one uh, 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 one part here with nine bonds. This asymmetric configuration is magnetic, it's semiconductor, and has a lower formation energy. So if you are creating vacancy and monolayer phosphorene, you are expecting that the SV59 configuration will be the most favorable one. And it is a good thing because you have a magnetic configuration here. Pristine phosphorene is non-magnetic. By creating a vacancy, a single vacancy, you can have a magnetic configuration, but with a quite high formation energy, 1.6 electron volts. And here is just the band structure of these configurations. See, on the left hand side here you have a pristine configuration that's non-magnetic and has a band gap of slightly above 0.9 electron volts. The middle panel here, it's the symmetric configuration with a single vacancy. It's metallic, you have bands crossing the Fermi level, and it's non-magnetic. And on the right hand side you have the asymmetric configuration, that's the most favorable one when you are creating a single vacancy. And you have a magnetic moment of 1 millibor per cell and a band gap of the spin-up channel of slightly above 1 electron volt. And this magnetic moment in this asymmetric configuration comes from this dangling bond of this atom 3 that doesn't bond. Because the atoms move in an asymmetric way to reorganize after the creation of the vacancy, you have a dangling bond in atom 3, and this generates the reason for the magnetic moment here. Now, if you look at the formation energy, what happened with the formation energy of these systems? Excellent, you can have magnetic configuration with single atom vacancy, but what happened with the formation energy of the system? So, when you look at the formation energy, we see that you can have a reduction of the formation energy when you apply a compressive strain. Here you see both biaxial strain, that's the black curve, and uniaxial strain along the zigzag direction, that is the red curve. You see a reduction of the formation energy when you apply strain. So you can have a system with a vacancy as stable as a pristine system here if you apply uniaxial strain along the zigzag direction, for example, the red curve. And also, you can have even a system that is more stable than the pristine system when you apply compressive biaxial strain. And this happens because you have the formation of a short-range ripple deformation in phosphorene when you apply strain. When you apply strain in a pristine system, you also have a ripple deformation, but it's a long-range ripple deformation. When you apply strain in the defective system, in the system with a single atom vacancy, you have a short-range ripple deformation. What's happening here is that the vacancy helps to accommodate the ripple deformation and reduces the formation energy when you compare with the pristine system, because the formation energy helps to accommodate the ripple deformation that happens when you apply strain in the system. And this is a good thing because, just let me back here a little bit, this is a good thing because now you can have a system that is as stable as a pristine system or even more stable than the pristine system, and you have a magnetic configuration here. So here is the formation energy. What happens if the magnetic moment in these systems? When you have a zero strain, you saw that you have, for example, for the SV59 system, you have a magnetic moment of 1 millibor per cell. That's what's happening here. This is the formation energy. So the magnetic moment, it was 1 millibor per cell with 0 strain. When you apply compressive strain, look at the negative side of this figure here, you see that the magnetic moment is still robust for uniaxial strain along the zigzag direction in the armchair direction. So, and for biaxial strain, you have a magnetic reduction. The magnetic moment keep robust around 1 millibor per cell, up to 6% strain, but then reduces to 0 magnetic moment. So what you can check from here is that when you apply strain in this SCV59 configuration, you have a stable system with a magnetic moment of 1 millibor per cell. So you can have a magnetic system for monolayer phosphorene, a stable magnetic system for monolayer phosphorene by combining single atom vacancy and compressive strain. But what happened here when you applied biaxial strain above 8% is that you have a closing of the band gap. The system becomes metallic. The band gap closes. You have a transition from semiconductor to metallic system under biaxial compressive strain above 8%. For the SCV5566 system, remember it was non-magnetic. The system was non-magnetic with 0% strain. But when you apply magnetic moment, uniaxial strain along the zigzag direction, compressive strain, you see that the magnetic moment goes up to 1 millibor per cell. And this also coincides with the range where the formation energy also reduces, and you can have a system as stable as a pristine system. And so, by applying compressive strain along the uniaxial direction, you can have a magnetic moment as high as 1 millibor per cell. And this also coincides with the opening of the band gap for the system. And now you have band gap higher than 0.5 electron volts for the system when you apply uniaxial strain along the zigzag direction, that are the red curves. What happened here is that when you apply for this system, if you remember, the SCV5566 was the symmetric system where the phosphor atoms moved to accommodate the vacancy in a symmetric way so that they formed the bonds. There was no Dunning bond anymore in the system, and so the magnetic moment was 0 with 0 strain. What happened when you applied uniaxial strain along the zigzag direction, let's say minus 10%, you pull apart these atoms and there is no anymore, they don't form bonds anymore. And so you have a dangling bond in the phosphorus here, and you have magnetic moment mainly come from this dangling bond. So let's move to what happened when we dope the system with carbon atom. So if you put a carbon impurity in this system, here is the green atom. So we are replacing a phosphorus atom by a carbon atom. You have less electrons now in the system here. So you have a magnetic moment, formation of magnetic moment here. And well, the system has quite high formation energy. It's not so easy to dope the system. So in the formation, the magnetic moment mainly comes from the carbon atom here. These are the magnetic moments in these atoms here, the carbon atom and the neighboring phosphor atoms. And this is a metallic system. You see bands crossing the firm level here. And again, the magnetic moment mainly comes from the p orbitals of the carbon impurity and the p orbitals of the neighboring phosphor atoms. This is an unstrained situation. Well, the formation energy was quite high with 0% strain, but again, when you applied compressive strain, you see that the formation energy goes down. And mainly when you apply biaxial strain, you can have a system more stable than the undoped system. And this is again because you have accommodation of the ripple deformation. Carbon atom as vacancy, the case of the single atom vacancy, it helps to accommodate the ripple deformation in the system when you apply strain. That's what I said. when you apply a strain, you see a short range ripple deformation when you have when the system is doped with carbon. So the magnetic moment was quite significant for the unstrained system, and when you apply compressive strain, you see the magnetic moment goes down, but when you apply biaxial tensile strain, you see that the magnetic moment increases. And this happens the same time that the system becomes semiconductor. You have an opening of the gap here, and you have a transition from metallic to semiconductor when you apply tensile biaxial strain. And this is not so bad because the formation energy, if you look in this top on the right corner here, you see that the formation energy doesn't increase that much with biaxial strain. So, summarizing here what you see, what I presented here, you saw that you can have a stable system, a stable magnetic system in monolayer phosphorene if you combine single atom vacancy with uniaxial strain along the zigzag direction. It's possible to have a magnetic moment of about 1 millibor per cell by combining single atom vacancy and compressive strain along the zigzag direction. And you can also have you can also induce magnetism in monolayer phosphorene when you dope each carbon atom and combine it with biaxial tensile strain. And that's all. Thank you very much for watching.